if she's there. Fiona, feel free to, great.
Go, and I better unmute myself or you won't be able to hear what I'm saying.
Better.
Great. Well, so since I'm the last speaker, let me actually start by just thanking all the organizers. You guys did a great job. And also all the other speakers. I really enjoyed listening to everyone's stuff. And yeah, so today I'm going to tell you about, you know, a story that kind of starts with the kind of anomalies in higher rank gauge theories that were featured in the last session, and a sort of analogous kind of anomaly that can arise in certain free fermion systems. So my talk is going to be primarily based on recent work with Taylor Hughes and his student Oleg Dubinkin, which was posted here. And so, so let me just quickly remind you, you know, look, anomalies in field theory, we now know have all kinds of interesting implications when we look at, you know, just free fermion models described by band theory. And so to, you know, remind you of arguably the simplest context where that arises, let me give you a very quick condensed matter person's take on the anomaly that Hotat was describing earlier. So here's this Lagrangian, okay, for a free boson. And, you know, as a condensed matter person, when I look at this Lagrangian, I think, oh, this is Lagrangian describing a bosonization of a one-dimensional metal, okay? And in that bosonized treatment, right, what we learn in graduate school is that the fermion, you know, the charge density of the fermionic system looks like dx phi, right? And so the corresponding conserved current is actually the kind of winding current in the context of Hotat's talk. And this is the one that's conserved exactly because by equality of mixed partial derivatives. And of course, this system has another conserved current, in which I basically flip the dt and the dx. And this one is conserved, but it's conserved only due to the equations of motion. And now a quick sort of cute little argument, which reveals the fact that these two guys have a 't Hooft anomaly, is let's imagine that, you know, I'm an experimentalist. I'm just going to put some electric field along the system in the x direction. And so I'm going to take my electromagnetic current and couple it to this classical background field A mu. And that modifies the equations of motion so that I can see that this other current is no longer conserved. And of course, in our lattice model, this is completely intuitive. We apply an electric field, and you know, I move states from the left part of the Fermi surface to the right part of the Fermi surface, and the momentum is not conserved under that deformation. Okay, and so now the kind of inspiration for this work was an anomaly that actually we first thought about in work with Taylor and Yiji. In which you know, we were actually thinking about higher order topological insulators, but you kind of naturally encounter an anomaly that's essentially this other 't Hooft anomaly of the higher rank, you know, so of the subsystem symmetric sort of phi theory here. And again, we have two conserved currents, right? One which is always conserved by equality of mixed partial derivatives, and one that's conserved only due to the equations of motion. And again, you can argue that if you interpreted this, if you interpreted this first current here, the one that's always conserved, as some particular combination of electromagnetic currents, and this AXY is some combination of electromagnetic gauge fields, or rather their spatial derivatives, that you get a modified equation of motion in which you see that this other current, okay, which cares about the equations of motion, is no longer conserved. So this is just, you know, some 2D system of bosons. Unlike in 1D, there's no obvious bosonized mapping that at least that I have worked out the details of onto a fermionic system, but we can nonetheless ask whether this kind of anomaly has some kind of analog or interpretation, you know, in systems that don't have any kind of exotic symmetries, such as maybe just band theory, okay? And so what I'm going to tell you about today is a context in which you have something not identical, but really very similar in spirit, with interesting consequences for these fermionic systems. So what we'd like to do is write down some kind of, you know, fermionic analog of this dispersion, okay? And so for fermions, the natural thing to write down is basically just kx, ky. Okay, and so for right now, these pictures, you shouldn't interpret them as representing a lattice model in 2D. This is just some, some picture of some linearized dispersion, and we're going to ask, what its properties are. Okay, and so here's a sort of picture of a system that has a dispersion that looks like kx, ky near the origin. Okay, and a feature that you notice is if I kind of look as a function of kx at the one-dimensional systems in the y direction, I see that when kx is positive, I have right movers in y, okay? And when kx is negative, I have left movers in y, okay? And so now you can ask, what happens when I apply an electric field, right? And so, just like in 1D, our electric field took left movers and reduce the number of left movers, increase the number of right movers. So the same thing is going to happen here. Okay, when I apply an electric field in the y direction, I'm going to create more particles on these right moving branches over here, and less particles on these left moving branches over here. Now you can see that as long as I sort of cut this box off symmetrically, in kx and minus kx, the total number of fermions in my system does not change when I do this. But of course, the momentum in the x direction is going to change because I'm essentially, you can think of this as transferring some guys from over here to over here. Okay. And so this looks a little weird, in one dimension we have this kind of, picture that things flow from left movers to right movers, but they do that through the Fermi sea. So this already looks a little weird. But if you're not convinced that this is sort of weird enough to rule this out as a two-dimensional system, let's consider playing a little bit with lattice defects. So what I could imagine is I'm going to take this system and I'm going to twist the boundary conditions on the torus by some amount delta. Okay, and if I do that, right, so I'm just basically changing the nature of the periodic boundary conditions. If I do that, I change the quantization of the momentum such that when I have twisted all the way around, right, so that the actual sort of points in the momentum space grid are the same, I have shifted each value of kx by something which is exactly, ky. And okay, so what happens when you do this? Well, this is, essentially like applying an electric field, if you like, that's proportional to ky. Okay, so in this case, you're going to see that you get, an increased number of fermions both above and below the point ky equals 0. And so this kind of twist violates charge conservation. So this is another manifestation of this mixed anomaly. And so just to summarize where we are so far, right, for a 2D system, I've shown you a kind of band structure which has an anomaly, which is a little bit different, but very similar in spirit to this mixed anomaly that we see in this higher rank, or this subsystem symmetric plaquette model, plaquette XY model. And so in particular, this guy has two, if you like 2 U1 currents here. And of course, it has subsystem symmetry. This model absolutely does not have subsystem symmetry. And also it has 3 currents, right? So it has charge and then it has momentum in each direction. But the fact that you get this kind of mixed to Hooft anomaly type structure is exactly the same. And so we would sort of say this has a similar spirit. And I'll say a little bit more about that in the bulk action in a minute. And so, okay, so this is the anomaly that I want to talk about. And another thing that we've learned, in the last decade or so in condensed matter is that if you find an interesting anomaly in some field theory, what you should try to do is write down some, bulk theory that's going to cancel it. And it's instructive in doing this to stare at this system and ask yourself why it's obvious, okay, that you can't realize this in 2 dimensions. And the reason that it's obvious that you can't realize this in 2 dimensions, just a single sort of crossing of this type, is that the Fermi surface is not closed, right? And so if I extend this picture out over some whole Brillouin zone, either I'm going to get other points like this, okay, where I have some, other points with some opposite, kind of contribution to the anomalies, Or of course I could, move these branches of zero energy modes off of the axes here, and I could close the loops in this way. But whatever you do, you can convince yourself pretty easily that the anomalies that I talked about will be canceled in 2 dimensions, simply because the Fermi surface is closed, and a closed Fermi surface does not, never has these kind of anomalies that I'm talking about. Okay, so what do we know? What bulk theories do we know that have surfaces, have boundaries with open Fermi surfaces? Well, obviously they're Weyl semimetals. So indeed, if you want to realize this as a surface state of a 3-dimensional system, the natural place to look is a Weyl semimetal. And there's something a little bit unusual about this Weyl semimetal compared to the ones that you're probably used to. So in a Weyl semimetal, we have Weyl points, and each Weyl point has a chirality, depending on whether that Weyl node is a source or a sink of Berry curvature. And so here, sources are colored blue and sinks are colored red. And normally when you think about a Weyl semimetal, you might only have 2 of these, and so you'd have like a blue one here and a red one here. And you could think of that as saying that these Weyl nodes have a dipole moment, okay? Now, in order to this surface state, without additional kind of anomalous charge responses, it's important that your Weyl semimetal have a quadrupole moment. So we don't want to arrange these in plus, minus, plus, minus. We actually want to arrange them in plus, plus, minus, minus, okay? And so this is a feature of time reversal symmetric Weyl semimetals, okay? And the dipole moment is going to vanish, and then the response of this system is described by the quadrupole moment of the Weyl nodes. So what is that response? Well, this is a free Fermion system. Okay, you can just go ahead and calculate linear response from the Kubo formula. And what you find is that the linear response is a mixed response between, and I missed a little A down here, but this is the electromagnetic current, and this should be a J mu A. These are the momentum currents, of which there should be 3 of them. Okay, and the coefficient Q here is exactly the quadrupole moment of these Weyl nodes. So specifically, this quantity chi can be plus or minus 1. That's the chirality of the Weyl node alpha. And capital K alpha here with the subscript I is the ith component of the locus in momentum space of the alpha-th Weyl node. Okay. And so what does this mixed response mean? Well, here, the electromagnetic current is sourced by this quantity E, which basically represents a lattice field, meaning that if we have lattice defects, those are going to give us fluxes in this guy. And the momentum current is sourced by the electromagnetic gauge field. So for example, you see sort of momentum density build up if you put magnetic fluxes into your system. And Oleg tested these numerically, and here's a nice picture that he made to show that that really happens in the lattice model. Okay, and so, finally, just to kind of close the loop and come back to things that look maybe a little bit more like higher rank gauge theories, you can encode this response theory in some kind of bulk action. And the simplest bulk action comes by imposing a mirror symmetry, which actually reduces the number of independent components of the quadrupole tensor to 1, okay? And in that case, my bulk action looks like this. Okay, so these epsilon guys are basically the analogs of the electric fields associated with lattice gauge fields, and these sort of curly B's are the analogs of the magnetic gauge fields. The magnetic field associated with lattice gauge fields. Okay, and this actually gives the correct response theory, and this also is. If you want to sort of think about the anomaly, it's easy to check that this theory is only gauge invariant up to a boundary term. And I think the interesting comment is, if you cut a boundary, say in the z direction, and you just looked at the term in here, the boundary term that you get from this action, it would look exactly like a boundary term that cancels this, the plaquette XY model anomaly if you thought that this particular symmetric combination of these lattice electric fields should be identified as some higher rank tensor gauge theory. So again, not the same. Sorry, Siri wanted to interject there. So not exactly the same, but very analogous. And so let me just kind of put up the morals of the story. So I think it's interesting, when we think about these subsystem symmetric systems and higher rank gauge theories, which seem like, maybe quite exotic things, that they do have analogs that turn up in the study of free fermion systems, such as higher order topological insulators and these sort of quadrupolar Weyl semimetals. A natural sort of context for this to happen is, what we saw in this talk, which is when you have sort of a mixed response between sort of momentum energy and electromagnetic field. So a sort of mixed response between lattice quantities and electromagnetic quantities. And that this leads to interesting, kind of physical properties in these systems, which maybe are not obvious or are more obvious when you sort of phrase things in this way. So I will stop there. And I guess we can take questions.
Thank you very much.